job's a joke, you broke. Your love life's the old way.
Hello, my name is Maya Nupp, and this is my 2019 science project for Mr. Caruso's class. There once was a man called Sir Isaac Newton in the 17th and 18th century. He was an incredible scientist who built off the ideas of Galileo and Aristotle. While sitting down on a hill, an apple fell down from the tree above him. Believe it or not, he was a very intellectual man, as you could tell. After realizing what had happened, he began to think, why does the apple fall straight down as opposed to forward or backwards? With that question, he discovered the law of universal gravitation. He also discovered the 3 famous laws of motion, Newton's 3 laws of motion, to be exact. Now let's start off with Newton's first law of motion. An object in motion stays in motion, and an object at rest stays at rest, unless acted upon an unbalanced force. It is commonly referred to as the law of inertia, which is the tendency to resist change in motion. Now what is this unbalanced force, you ask? Well, there are 2 different forces, balanced and unbalanced. When an object's motion is acted upon by a balanced force, the object's velocity does not change. So if the object is in motion, the speed will stay constant and in the same direction. If at rest, the object won't move and will remain at rest. For example, Johnny is trying to push a box to the right, but Bobby wants to push the box to the left. They both push with a force of, let's say, 55 newtons. Their forces will cancel off each other, and there will be no net force. That means the box will not move left or right. When an object's motion is acted upon by an unbalanced force, it can change the object's speed, direction, or both, whether it be in motion or at rest. An object in motion will accelerate or change its direction. An object at rest will move in whichever the direction the force is pushing in. The velocity can change depending on which of the said forces is greater. So let's say that Johnny has been hitting the gym for quite a while now and is really buff and beefy. And Bobby has just been sitting and playing games all day, not doing homework, not doing any exercise, so he's getting fat. And they push the same box as before. Johnny is pushing it to the right with a force of 100 newtons, and Bobby is pushing it to the left with a force of 25 newtons. If we take the greater force and subtract it by the weaker force, and add the direction of the greater force, it'll give us our net force. The net force will be 75 newtons to the left, allowing Johnny to, destroy Bobby. Another example could be that a ball is rolling on a frictionless surface, which basically means that it won't stop due to the surface friction. The ball is going about 1 mile per second constantly, which is pretty fast. Then a fan is placed behind the ball, which increases it to 3 miles per second. Now, let's continue on to Newton's second law of motion. The acceleration of an object is directly proportional to the net force and inversely proportional to its mass, or better known as force equals mass times acceleration. This one is pretty simple to understand, but first let's go over what directly and inversely proportional means. Directly proportional is when both variables have a constant multiple. So if x goes up, y goes up. If x goes down, y will also go down. Inversely proportional is when 2 variables equal to a constant value. Whenever x increases, the y will decrease, vice versa. Now, let's put this into perspective with Newton's second law of motion. If mass stays constant in the equation, acceleration and force will proportionally increase and decrease with each other. A 25-kilogram ball is rolling on some ice with an acceleration of 30 meters per second squared. If you multiply the 25 kilograms and 30 meters per second squared, you'll get 750 newtons. If the acceleration increased to 40 meters per second squared, the force will increase to 1,000 newtons. This will be the same if the acceleration stayed constant. Force and mass will be proportional. They are directly proportional to the force. Now, if the force stayed constant, the mass and acceleration will be inversely proportional to each other. Mass and acceleration will have to be multiples of the force when it's at a constant. Let's say the force of the ball is 30 newtons. Then the mass of the ball could be 1 kilogram to the acceleration of 30 meters per second squared, or a mass of 2 kilograms and an acceleration of 15 meters per second squared. As you saw, when the 1 kilogram increased to 2 kilograms, the acceleration decreased from 30 meters per second squared to 15 meters per second squared. Last but not least, Newton's third law of motion. For every action has an equal and opposite reaction. The law is just as it says, equal and opposite reaction, which means forces will always come in a pair that is equal and opposite to each other, which is what we call a force pair. There's two parts of a force pair, action force and a reaction force. The forces in the pair will not cancel out each other because it is not acting on the same object. It's acting on two different objects. When a hammer hits a nail on the head with a force of 400 newtons, the nail exerts the same amount of force back onto the hammer, 400 newtons. That's why the hammer does not bounce back when it hits the nail. A key term in the third law is conservation of momentum. First, let's define momentum, a measurement of how hard it is to stop a moving object, which is momentum equals mass times velocity. The conservation of momentum is when two or more bodies act upon one another. Their total momentum remains constant provided no external forces are acting, which is total momentum equals total momentum after. Now let's say two 2,000 kilogram cars charge at each other head on. One of the cars is going 40 miles per hour to the right, and the other one is going 20 miles per hour to the left. When they collide, the cars go in the opposite direction than when they were before the collision. The one on the left now has a 20 miles per hour velocity going to the left, and the one on the right has a 40 miles per hour velocity going to the right. If you plug those into the equation, the two momentum before and after will be the same. That's an example of conservation of momentum. Newton's laws of motion were revolutionary in the world of science. I guess we should all thank the apple for bonking Newton on the head, but in reality it didn't hit him on the head, it fell in front of him while he was working on a hill. I know, it's boring, it sucks. Well, you know.
Whatever happened to predictability? The milkman, the paper boy, evening TV.